All right, you guys, I just want to give you a quick explanation about faults. Now, what we're doing is we're looking at a cross section here. If you were walking, you'd be walking up on the surface here. And so this is a cross section through the earth. And what we have are faults, and faults are breaks in the rock across which motion occurs. Now, until I move these blocks in a number of different ways, they're just joints or cracks in the rocks. In order to be a fault, you have to have movement across the break or across the fault. All right, so in order to talk about what's called dip-slip faults, okay, or where the movement is vertical, we have to be able to identify two different parts of the fault. So I'll go down to two blocks right now. Now, this is what's called the hanging wall block part of the fault, and this is the footwall block. Now, the hanging wall block is the part that hangs over the fault. And also, if you were going to play hangman, think about it. You could only hang hangman off of these two sides. You couldn't hang him off here. You just sit here and not die. So if you want to play hangman, you got to play it on the hanging wall block. All right, in order to understand what type of fault we have, you have to know if the hanging wall block went up relative to the footwall block or if it went down. Now, I'm going to start with a fault type called a normal fault. And normal faults are what we're going to find in the Basin of the Range, which is just to the east of the Sierra Province. And what happens is that when when the plates are pulling apart, it's an extensional force, okay? And we talked about that. Divergent boundaries have extensional forces, or big arrows pulling apart. This block will slide down. And so you get what's called a normal fault. And in a normal fault, the hanging wall block has dropped relative to the footwall block. Normal fault is the arrows are pulling out. The footwall block is here. This is the hanging wall block, and the hanging wall block just basically drops down and makes the basin. All right, let's put it back to the original configuration. Now I'm going to do a compressional fault. And so at plate boundaries where the plates are crashing into each other, we talked about convergent plate boundaries, but this is called a compressional fault. And this is called a reverse fault. And these are the type that we have locally up in Auburn. So when I squeeze these blocks together, the hanging wall block now moves up relative to the footwall block. Okay, so hanging wall block moves up. You can see that it's shortened and thickened. So you find these at subduction zones. You find these at continental-continental collision. There's a lot of reverse type faults in the Himalayas. All right, we got to now take a bird's eye view, so you guys will recognize this is the stream here. Okay, and remember, we were looking at vertical offset, but now we're going to actually look at horizontal. So it's just a crack until there's horizontal offset. And this is actually the type of fault that we have in California. We have a horizontal fault. We have the San Andreas Fault. Okay, so I'll go back down to two. Now, you guys, they're either right-handed or left-handed. And what you do is you picture yourself standing on one side of the fault, looking across at the other side, and that feature, the river here, stream, has been offset to the right. And it wouldn't matter if you came over here now and you're standing over here. Hey, where'd my stream go? It's been offset to the right. Now let's make a left lateral fault. The San Andreas Fault is a right lateral strike slip or strike slip fault. So again, here's my feature. I'm looking, hey, where did my stream go? Oh, it's off to the left. You're over here on this side. Where did my stream go? Oh, it's off to the left. So those are your three different types of faults.
intercontinental smash began to shape the world's highest mountains. Traces of the first stage in this process can still be seen in the Himalayas today. The best way to spot them is from the air.
Because the high Himalayas are so incredibly inaccessible, I mean, just look at that view out there. There's a sea of mountains, all of them are over 20,000 feet. There must be hundreds of them. And those are impossible mountains for a mere mortal to climb.
This is geology on a massive scale. The distinctive formations come into view. Huge folds of rock, clearly seen on the sides of the mountains.
All of these folds that we're seeing right here on Dhaulagiri and Tukche Peak were formed during the first part of the Himalayan mountain building process. So when India first collided with Asia, the first thing to happen was that the northern margin of India started buckling and folding. And those folds are just so spectacular. When you look out the window here, they're just unbelievably impressive.
Like a giant train wreck, India collided with Asia. The land and ocean floor that lay between literally folded up under the enormous pressure. But folds are only part of the story. Searle points to an intriguing giant scar which is revealed on the face of one of the mountains. It's evidence of the next dramatic phase in the building of the Himalayas.
This is a sketch of what we're actually seeing in front of us, with the big mountain of Dhaulagiri here and the big folds on the peak of Tukche to the right, with this enormous great fault that is magnificently exposed right along the base of Dhaulagiri, coming right down to the Kaligandaki river valley at the bottom.
The fault is a fracture running right through the mountains.
Well, the first step in deforming the Himalayas is that the rocks are folded into giant folds. And when that process continues, the rock can no longer fold, so they become overturned folds. And when the process continues even further, that overturned fold actually moves along a very discrete fault plane. And that's exactly what we see throughout the whole Himalayas. So rocks are formed by folding and thrusting.
Rocks can only be bent so far. Once rock has been bent beyond its limits, it breaks and causes a fault. The process of faulting puts different rock types one on top of the other.
This box is a replica of a model that the Victorians used to explain how sideways movements built mountains. Just putting a layer of black sand along the base of the box here. And that's going to be our first geological layer. God, I'm going to have to get a move on. Oh man, eh? These sand layers represent the mountainside behind me. Now I'll just put the lid on. Now what I'm going to do is turn this wooden handle here, which is going to turn this screw and send these wooden blocks into the layers, as if a great sideways force is crashing in. I'm going to do it really slowly though. Here we go. Here we go. There she goes, look at that. It actually works. You can see that this slab of rock strata has been thrust up and over on top of this slab of rock strata, which is exactly what Lapworth was saying. That is beautiful. I never thought it'd be this good. A whole series of zigzags are forming. And what we're doing, most importantly, look behind, we're building mountains. And the point is that is exactly what's going on over there. Get out of here.